And we're back for more. Today we're talking about the simplest formula, but before we do that, I want to ask you a question. In what kind of consumer products would you find on the ingredient list brominated vegetable oil? Brominated vegetable oil. We'll talk about it at the end. Let's go back to simplest formula. The name, if you were to check your textbook, the name that your textbook is going to use for this is empirical formula. And empirical in science is used to mean observable, the observable formula. Not quite what you might be thinking in terms of the observable formula, but we'll try and fill in those gaps as we go along. Remember where we started from and where we're trying to go with this. We've already done percent composition by mass, which of course is the ratio of masses between atoms in a compound. The problem with that is when I write a chemical formula, let's say H2O, I'm not talking about the mass of hydrogen in water, I'm talking about the number of atoms of that. So that's a gap we need to bridge. And our first step in that is the simplest formula, SF. And that's the lowest mathematical ratio of numbers of atoms. Now, the important thing about this is it's a mathematical relationship. It's not necessarily going to be the actual chemical formula. That's going to be something that we have to figure out later. But for an example, this compound here with 6 carbons, 12 hydrogens, 6 oxygens, that's a real chemical formula. That's an actual compound. And if you've taken biology, you may have come across that. There's several sugars that have that, but the one I was thinking of is glucose. You don't need to know that, so you don't have to write that down. Mathematically, the ratio of atoms here, 6 carbons, 12 hydrogens, 6 oxygens, mathematically that could reduce to 1 to 2 to 1. It doesn't mean that there's any chemical relationship, any chemical similarity between the actual formula on the left and the simplest formula on the right. None whatsoever, but there is a mathematical relationship. Finally, and this is going to be our next step, we're going to come up with a molecular formula, and that will be the actual chemical formula, the actual ratio. So for example, our glucose molecule, again, that is the real chemical formula. Now, our last job will be to go from our simplest formula to our molecular formula, but we're not going to worry about that right now. We're going to focus on simplest formula to start. To give you a look at how they're related, and you don't need to write this down, I know some of you take really awesome notes, but just to kind of give you several examples to compare real formula to simplest formula, mathematical lowest ratio. So we have this one here, tin 4 oxide. Well, that is the simplest formula, which should make sense because in nomenclature, when we were doing metal, non-metal compounds, it was always crossover and reduce. So we were always writing the reduced formula. Water, molecular compound. Well, in this case, it's a fairly small compound, and it does have the simplest formula, which is the same thing as the molecular formula. On the other hand, dinitrogen tetroxide mathematically reduces to NO2, not chemically related. This one here, C8H18, is actually octane, and it's a real chemical formula, a real compound, to this one here, C4H9. If you were to try and draw a Lewis diagram of C4H9, you would get stuck. It would not work. That's because C4H9 is a mathematical thing, not a chemical thing. But again, that's going to be where we end up today. And two more, this one. Again, you would not be able to draw a Lewis structure for that, not one that would work anyhow. And then lastly, iron 3 oxide. Now the other thing I want to look at with this is as we go through the simplest formulas and look at the ratios of atoms, 1 tin to 2 oxygens, 2 hydrogens to 1 oxygen, 1 to 2, 4 to 9, 1 to 1, and 2 to 3. You'll notice that for most of them, one of the atoms is a 1. Not all of them, but, oops, sorry, that's a 9. Not that one either. Let me take those away. So not that one. But for most of them, there's a 1 in the simplest formula. Doesn't matter for right now, but in a couple of minutes that's going to come back and we're going to remember the significance of that. There are steps. It's a mathematical formula. There are mathematical steps. We're going to go through the steps right now, and then we'll walk through a couple of examples together. Walk through one example anyhow, and then we'll sort of do half of one together. So let's get our steps. Use the percent composition values as masses. You'll be given percent compositions in the question. Take those numbers, they're out of 100, take them as masses. So if it's 30%, call it 30 grams. Calculate the number of moles of each. Now we know how to do that. Number of moles is the mass, right up here, divided by the molar mass. Then we're going to take those numbers of moles and we're going to divide by the smallest number of moles. That sounds like a little strange right now, but this step is kind of key. So don't worry about putting a little star beside it or anything else like that. It'll make some sense in a few minutes. And then finally, step number 4. Step number 4 is where we're going to hit the wall in some cases, because we have this statement here, if it's not easily roundable. Well, what does that mean? Then I'm going to multiply by 2 or 3 or something else. Again, once we get there, it should make some more sense, so just hang on. Step number 4 as it is. The bottom line, though, is most of these things will be fairly easily roundable. In other words, it'll look obvious that it's really close to a whole number. If it's not close to a whole number, it won't be even remotely close to a whole number, and then we'll have to do something to fix it. So here's an example. Here's a very typical kind of question. You're given percentages. You're asked to find the simplest formula. Okay, so you got the question down. I'll show you we'll walk through the steps. I'll show you how to lay it out so that it makes a lot of sense, at least to me. We'll go through it slow time, and then I'll show you what would be the bare minimum that you'd have to show me in an answer. I like a table. I like to put the atoms that I'm talking about across the top, so carbon, hydrogen, nitrogen, and oxygen, and I start right away labeling it on the far left-hand side. So the percent composition numbers, which were in the question, they're now my masses. Step number 2 said take that and convert to the number of moles, so calculate number of moles of each. That means divided by the molar mass. So I want the molar mass of carbon, I want the molar mass of hydrogen and nitrogen and oxygen. So divided by 12, divided by 1, divided by 14, and so on. That calculates out the number of moles. Now you'll notice that right now I have a ratio of moles, but not a very convenient one. You'll also notice that down here I've got 3.91 moles, 6.25, 1.56, 1.56. It won't always happen that two of them are the same, but with these two that are the same, or at least very, very close to it, rounded off the same, they're smaller than the other two. That's important because my next step was divide by the smallest. So I'm going to divide everything by 1.56. So divide all of them by 1.56, and I got 1, 1, 4, I'm working backwards of course, and 2.5. So this probably wasn't exactly 4. If you were to push the buttons on your calculator, maybe it would be 4.01, maybe 3.99, but it was easily roundable. The one that's not is 2.5. Now I know that in math you're allowed to round up from a 0.5, but in chemistry, in this stuff, it's going to work out much closer than that. So this is not easily roundable. So now what? Well, now I'm looking at step number 4, which said if it's not easily roundable, then I'm going to multiply by 2 or 3 or, well, how do I know what to multiply by? Well, quite easily, I'm trying to get whole numbers. If I multiply that by 2, I'll get a whole number. So that's what I do. Well, if it were, say, 2.33, okay, now I'm going to multiply by 3 to get a whole number. There's not too many other possibilities. Usually it's a multiply by 2, maybe a 3. Once that happens, I have whole numbers. And now I want my formula to have whole numbers. I'm at the point where I'm ready for my simplest formula. Simplest formula, I take the numbers that I came up with in my table and I put those into the formula. Bare minimum expectation, because all of this stuff, I mean, we've got it labeled nicely on the left. We've got numbers all over the place. Some of them we need, some of them are for us to learn, but not so important once we know what's going on. So bare minimum table, you would have a row of masses, you'd have a row of moles. The only way to get from your mass to mole is divide by molar mass. So I'm going to assume that if you've got the correct number of moles, you divide it by the molar mass. Dividing by the smallest. You've told me what you're doing. I can see on your table which one is the smallest, so I can easily assume what you've done and multiply by 2. So you've told me on the left what you're doing. All I need is to see these big numbers in the table. Okay, here's a question to try. And what I'm going to suggest is you try it, pause it, right, get the question down, pause it, try it. I'll show you a partial table just to make sure that, as you filled in, we can compare your answers or some of your answers with the answers I'm going to show you. Okay, I've talked long enough. Here's the table. So we start out with our masses. We divide by the molar masses. Now this line here, of course, in the middle, or with divide by molar mass, that does not need to be part of your final table. So if you're not including it in yours, no problem, but you will get this as your number of moles. And of course you'll do 23.7 divided by the molar mass of sulfur, and so on. Once you go through, you identify which one is smallest, you divide by the smallest, and we have a 1 right there. Okay, so you need to fill in that spot, and the last two. Probably in a bit of different order than I've got them circled. When you've done that, you'll end up with a simplest formula of KSO4. Okay, a couple more. I'm going to start class by checking these, so get the questions down, try and answer them out. At least follow the steps, you can't go wrong. If you do get stuck, we'll talk about it in class, but the simplest formula is a fairly simple thing to do. Back to our brominated vegetable oil. Brominated vegetable oil is vegetable oil, like any other kind of corn oil or soybean oil or whatever, but it's had bromine atoms added to it. And what that does is it changes the density of the oil. So oil normally floats on water. Brominated vegetable oil doesn't. It has the same density as water. So it won't mix with water, but if you were to shake it up, it would not form a layer on top. Why would they do that? Citrus flavored soft drinks, some of them anyhow, have citrus flavoring that won't mix with water. It would form the layer on top, but it will mix with the oil. Remember, likes mix with likes. So the citrus flavor mixes with the oil, but now that's going to float on top. Okay, so when we add bromine to the oil, and that makes it heavier. So now the brominated vegetable oil with the citrus flavors will disperse, not dissolve, but disperse. One is polar, water, and the oil is nonpolar, but it will disperse. Well, it ends up making it look kind of cloudy, which some people think is a good thing because now it looks a little bit more natural. Think of regular orange juice. Now, I don't want to give you a list of places where you would find this, a list of products, just in case somebody from Greater Aid is watching. I mean, these things could be that popular. No. But is it safe? That becomes the question. Well, like anything else, in certain amounts, yes, certain amounts, no. Canada and the United States have decided that in the amounts that a regular person would probably drink, yeah, they are safe. Some European countries, and I believe Japan also, say, no, we don't want those things in our water. So there are other options, or not in our water, in our soft drinks. So there are other options. Now you know. We'll talk to you in class. Make sure you have these questions ready to go so I can check them. And we'll talk to you about stuff later. Take care.